Okay, so first of all, here's your Turing machine, right? So this is the tape. This is the first program, the program that computes the computable number 1/3. So you started on an empty tape. You put it into state 1, okay, and then you run it. But because this is our first run of a Turing machine, let's do it slowly, right? So the Turing machine has two instructions. The instructions say if you're in state 1 and you're reading a blank, then write a 0 and move right, and then go into state 2. Right? So our Turing machine is now in state 1. It's reading a blank. So what it does is write a 0 and then move 1 to the right. Let's see if that's actually what it does. Yes. Okay? So now the Turing machine is in state 2, and it's moved 1 square to the right. It's reading another blank. And the instruction set of the Turing machine says, if you're in state 2 and you're reading a blank, then write a 1 and go 1 square to the right and return to state 1. Okay? And now again, we're reading a blank. We're in state 1. We're going to write a 0, move 1 to the right, and so on. Right? So let's see what the Turing machine does if we just keep running it. There. It computes 1/3 in binary. Okay. Now the other Turing machine here, right? That's a Turing machine. That's the program for the Turing machine that tests whether a number is even. It's a Turing machine that's supposed to do that when you run it on a sequence of 1. So in this case, we have 2, 4, 6, 8 ones, right? In the end, we want there to be only a single symbol on the tape. And that symbol should be 1 if the input is even, and it should be 0 if the input is odd. So let's see what it does. Oops. First, I have to put it into the right state. So in state 1, starting on the leftmost square of the tape. Ta-da. Right? Correctly figured out that 0 is, that 8 is even. Right? And in the end, it's in a state 3, and the instruction set doesn't have any instructions for what to do when you're in state 3. So it doesn't know what to do, and that's when the Turing machine halts. All right. Good. So that's what a Turing machine is, and that's how Turing machines compute computable numbers. Now we actually want to use this method of or this sort of notion or this analysis of computability to prove things about certain decision problems. And the first observation, and that's one of the crucial and important contributions that Turing made in that paper, was that you can code the instructions of Turing machines as numbers. It's not I mean, once you know how to do it, right, it's not a terribly deep idea, right? Because what a Turing machine is just a sequence of 5 tuples, right? Each instruction consists of a state that the Turing machine is in, a symbol that the Turing machine is reading, and then a symbol that the Turing machine is supposed to write, and then a direction in which the Turing machine is supposed to go, and then the state in which the Turing machine is supposed to end up, right? And of course, you can. There's only finitely many states and only finitely many symbols. So you can assign numbers to code these 5 tuples. And the coding that Turing himself chose was to assign to a 5-tuple, a quintuple I, Sj, where Sj is the jth symbol in the list of symbols, Sk, where Sk is the kth symbol in the list of symbols, then L or R, and then the number of the state that the machine is supposed to end up in. The following number, right? The number that you get in decimal representation, for writing 3, and then I1s, and then another 3, and then J2s, and then another 3, and then K2s, and then either a 4 or a 5, depending on whether the machine is supposed to go left or right, and then another 3 and M1s. Okay, so that's the code for a single instruction, and an entire program is just a list of these instructions. So the code for a Turing machine program is just a list of all these numbers that correspond to the individual instructions, separated by a 7. So for instance, This down here is our Turing machine code for the machine that computes 1/3 in binary, and its number in Turing coding is this very big number, which I can't read out, right? But and the coding is affected by assigning blank to be the first symbol, and 0 to be the second symbol, and 1 to be the third symbol. So you can describe Turing machines. That's not the important thing. Really, the really important thing now is that Turing also figured out that there's a single Turing machine which basically can do anything that any Turing machine can do. And it does that by taking as part of its input the description or the code of a Turing machine. Right? And that's the so-called universal Turing machine. The universal Turing machine U takes as input a number that codes, according to that coding on the previous slide, a Turing machine program. And then whatever the Turing machine that the code of which we've written on the tape, whatever that Turing machine does on the rest of the input, the universal Turing machine does on the input code of that Turing machine plus the input. Right? So if, for instance, the Turing machine T computes a number, then the Turing machine started on the empty tape, right? Then the universal Turing machine started on the code of T as input, will compute the same number that T would have computed if you just had run T. Okay? So that's sort of the first, one of the first, or perhaps the first example of an interpreter, of a programming language, right? So the description, or the description of Turing machines by numbers is basically the programming language, and the universal Turing machine itself is an interpreter for these kinds of programming languages. Carry out exactly what the program says should be carried out on the input. Now, once you can do that, it's only natural to then ask, well, what kinds of things can we, for instance, what kinds of questions can we decide via Turing machines? Questions about other Turing machines, right? Because the Turing machine program, the Turing machines can be identified with the representation as numbers of their program, and then these numbers might be fed as inputs into Turing machines. And so, for instance, the hope might be that there's a Turing machine that figures out certain things. So, for instance, a Turing machine which, given the code of another Turing machine, tells you whether that other Turing machine actually computes a computable number. So, whether it writes an infinite number of zeros and ones on its tape when you start it on the empty tape. Turing machines of that sort, Turing called circle-free. So a circle-free Turing machine is one that computes a computable number. Or the question, does the Turing machine T ever write the symbol 0 on the tape? Right? And we want to know whether there's a Turing machine which, given the code of T, will eventually end up with an empty tape, except for a single square, which is either 0 or 1, depending on whether the Turing machine T doesn't or does write eventually the symbol 0 on its tape. So those decision procedures in general are solvable, or we call them solvable, if there is a single Turing machine which computes, which solves them, which, given the input the number of the Turing machine eventually will produce 1 or 0, depending on whether the Turing machine with that code has the property in question, whether, for instance, it produces a computable number, or eventually writes the symbol 0, and so on.